All right, you guys, today's topic is section 1.3, units of measurement, and 1.4, over accuracy and precision. So we're going to start out with units of measurement here. This is the metric system. So there's two different systems that they talk about down here. English, which we use, the English system in some of Africa, and then most of everybody else uses the metric system. You sometimes hear it called the SI system. It's just kind of a unit that is based upon a derived metric system. So it's actually a lot easier to work with, which you're going to kind of see, and you worked with it before. So once we dive in, you'll kind of recognize some of this stuff. So starting out with these figures here, the fundamental units up here, so the different units that we convert between, you'll see some of these this year, but not all of them, like mass, length, time, temperature. You may see electric current, but if you were in a Gen Chem 2, you'd see that a little bit more. You're definitely going to use the mole this year. We probably will not get to the luminous intensity, but these are just different units that can be used for this. So mass usually is kilogram, length is usually meter, time can be seconds, but as you know, like time, there's other units that we can convert to. So what we're dealing with in the metric system, and I probably explain this a little bit different, so I'm going to highlight something for you, and I'm going to do green. So this line right here, if I can highlight it correctly, that's kind of like the base. So if you see the number is 1 there, so anything above that base, these are going to, and I don't know where I want to write this without, so I'm going to have to write on this a little bit later. So these are larger units up here. And then down here, these are going to be smaller units. And you've probably heard of some. Like, if I have meter, let's just take length. If I have meter, I can have a decimeter, I can have a centimeter, I can have a millimeter, micrometer, nanometer, picometer. I'm looking at these smaller units here. And then above that meter, I have a decameter, I have a hectometer, I have a kilometer, I have a megameter, and I have a gigameter. Those are larger units. So the base unit is 1. And what I kind of work off, if you look at these exponents down here, when they say 10 to the negative 1, I think of this a little bit different. I like to think of it by saying I think of the smaller unit. There are 100 centimeters in one of my base units. So I kind of work with it that way. I always have the number and how many zeros, because if you look at centi, it's 10 to the negative 2, meaning you add 2 zeros as you go to the right. So there's 100 centimeters in a meter. But up above, if I look at kilometer says 1,000. That doesn't mean there's 1,000 kilometers in a meter. It means there are 1,000 meters in 1 kilometer. So because kilometer is the bigger unit now. So it depends on where I am based on that green highlighted section there. So what you guys probably learned last year is you had the base, and I'm going to try to draw this up here. My stylus, again, doesn't work with me all the time. So if I have a step right here, and I kind of start here, if this is my base, so one below base was deci, and this was centi, and this was milli. And then when you went up the staircase, you went up 3, and this was kilo. Well, this year, you're going to have to learn some more. They go above it. Like if you look at kilo, above kilo is giga, and then, or mega, sorry, and then giga, and then tera. And you got to think about how many zeros. Above kilo, there's actually 3 more steps up to mega, and 3 more steps up to giga. And then where I'm at on milli, if you look at between deci, centi, milli, it's -1, -2, -3. That means there's 1 step in between them. But when you go from milli to micro, you jump from -3 to -6. There's actually 3 steps more down. So it goes micro, and then 3 more steps to nano, 3 more steps to pico. You're pretty much going to have to make conversions between, I would say, giga and pico is what your range that you kind of need to look at. So you used the stair step last year. If you want to continue doing it, meaning if you had like 0.5 kilometers, and I asked you to convert that to centimeters, what you did was you'd say, well, I'm at kilo, I've got to go 1, 2, 3, 4, 5. If I wanted to go to centi, and I move my decimal 5 to the right, so you'd say 1, 2, 3, 4, 5. And you'd have to add these zeros. That's fine if you want to continue to do that. The problem is you're going to have this stair step memorized. So it's fine if you want to do that, as long as you can write the whole stair step. So I may, if I can add, I think I'm going to add a new slide. No, we'll come back to that later. Maybe in the end I'll add a slide if you decide you want to do the stair step and you can actually I'll draw the entire stair step so you can kind of see it. But I'm going to move on and I'm going to kind of show you how I make these conversions. I don't use the stair step because I don't want to draw it out every time. I just think of this as a dimensional analysis thing. So when I look at these conversions down here, it says how many nanometers are in 3.7 meters. So again, I'm thinking of this as dimensional analysis, and we're going to work on dimensional analysis again. So the better you get at this, the easier it becomes. So if I have 3.7 meters, what I'm asking you to do is convert from meters. So meters would have to go on the bottom to cancel, and you would have to go to nanometers. So again, I think of the smaller unit as having the number with it. So when I look at nano, in the chart up above, it does say 10 to the negative 9th. But what that means, if you truly think about this, is that is, I don't know why my stylus is not cooperating with me. That is 9 zeros. Because nano is down here at the bottom of the staircase. I'm moving to the right, so I have to add zeros. So there are, I have 9 zeros there. That's how many nanometers are in 1 meter. So the number, the big number, is going with the nanometers. So I'm saying how many are in one of my base. So what I mean is 1 meter has, I'm going to go ahead and put it in scientific notation, has 1 times 10 to the 9th nanometers. I'm not going to write all those zeros. That's why we did scientific notation. So at this point, all I have to do is convert that and say, well, 3.7 times 1 is what? Well, 3.7 doesn't have an exponent. So that's just going to be 3.7 times 10 to the 9th nanometers. Nanometers would be my answer there. So on the next one, I'm going to do in a different color. If I've got 7.5 times 10 to the 15th picoseconds. Okay, well, pico, again, is at the bottom. It's below nano, where I just worked with. It is 10 to the negative 12th, meaning there are 1 times 10 to the 12th picometers in one base, in 1 meter. So but this time I've got to put my picoseconds down here. And again, the unit doesn't matter. Up above I used meters. It's all about the prefix that's going in front of there. So am I talking picoseconds, picometers, picoliters? Doesn't matter. I'm looking specifically at this prefix. So I want to convert picoseconds to seconds. Well, again, seconds is the base. So I'm going to say one base. One base has how many picoseconds in it? Well, again, picoseconds is a smaller unit. So there's going to be 1 times 10 to the 12th picoseconds in one base. There's going to be a whole lot of those smaller units in the base. Well, now I'm looking at reviewing my scientific notation rules that I've already got. Well, 7.5 divided by 1 is 7.5. And then when I'm dividing, what I do is I subtract my exponents. So I take 15 minus 12, which would be times 10 to the 3rd, and that would be me converting that to seconds. So that's how you do those. All right, on the next page, I'm asking how many kilograms are in 466 grams. So here I'm asking you to go above the staircase. Those grams, gram would go here to cancel. I want to go to kilograms. Well, now I'm in a different scenario. Now if you look back at your chart and your notes, I'm above the staircase. Kilo is the larger unit here. So now I've got to say the larger unit is going to have the 1 in there because it is the larger unit. So 1 kilogram, well, what number is associated with kilo? It's 1,000. There are 1,000 grams in 1 kilogram. So this is going to allow the gram unit to cancel. So 466 divided by 1,000 is just going to be 0.466 kilograms. And again, if you're doing the stair step, what you were doing is the decimal was at the end of the number. You just moved it 3 to the left because you're going up 3 stair steps. So you can kind of check yourself because a lot of you guys did do well with the stair step, but just kind of double check your work here. All right, the next one, the last one is going to be kind of a little bit different here because I'm not asking you a base unit here. I'm saying how many micrograms are in 8.9 kilograms. So if you stair step it, you just have to count the number of steps. But if you're doing dimensional analysis, and I think about this, I don't know how many micrograms are in a kilogram. I do know how many grams are in a kilogram, and then I can think how many micrograms are in a gram. So I would put this in 2 steps, and I would say, okay, well, kilogram needs to go down here to cancel. Gram would go up here. We just did this up above. Kilo is the larger unit. So 1 kilogram has 1,000 grams in it. That cancels kilograms, but now I need to look at micrograms. And I need to look at the number that's associated with micrograms. Well, gram is going to go down here to cancel. Micrograms, it's like a cursive M. It's kind of weird. Milligrams would just be an M. This looks kind of like a cursive U or a squiggly M. I don't know how you would describe it, but it does look a little bit different. Okay, so micro, if you look at it, is 10 to the negative 6th. That means you go 6 stair steps down, below base. So let's think of base. If I'm below that base, I think, okay, 1 gram, 1 base unit has how many of those little bitty units in it? Well, it's 1 times 10 to the 6th. There's 1,000,000 micrograms in a gram. So there is my setup for this. So I've got 8.9 times 1,000, and then times 1 times 10 to the 6th. So 8.9 times 1,000 is 8,900, times 1 would still be 8,900, times 10 to the 6th. Well, then we're looking at, we need to make sure that we have this in correct scientific notation. Decimal is at the end, so I'm going to say 1, 2, 3. I have 3 more exponents. So I'm going to say 8.9 times 10 to the 9th micrograms is what I'm dealing with here. And how do I know that I'm correct? Well, I know that kilo is an extremely large number and micro is an extremely small number. So I should have a big number in the end if I'm going from a bigger unit to a smaller unit. So another thing that I kind of threw in here, just so you guys kind of know, we deal with derived units. We may have to find density. We may have to find volume. There are different units that you're going to see for volume. You may see meters cubed, decimeters cubed, centimeters cubed, milliliters, or liters. We'll be using all of these. So some important things, and you may want to highlight this in your notes. 1 centimeter cubed is always equal to 1 milliliter, which is also equal to 1 gram of water, because the density of water is 1 gram per milliliter. So we can say 1 milliliter of water is 1 gram of water. Those kind of go, you just kind of have to, those are things that you have to memorize and just be able to use as we go through this. All right, the next section is over uncertainty and measurement. We're looking at precision and accuracy. They are defined down here. Accuracy is a particular a value that you get and you compare it to a true value. So it's basically how close is your measurement to a true or accepted value. And then precision is how close a series of measurements are to one another, meaning if I take 5 different measurements, how close are they to each other? So what we have up above is I've got a bullseye. So you've got to kind of be able to look at these, and I kind of go through them down here. The left one, this picture right here, that's if I'm looking at a bullseye, the target right in the center, that's my accuracy. If I can hit the bullseye in the center, then I know I'm accurate. Well, in that case, there are none of them that are hitting that, and none of those measurements are close together. All of those arrows are just all over the place. So that one, you would say, it's neither accurate nor precise. It doesn't have any of those capabilities. There's no reliability in those measurements. And then the middle one, they're not hitting this bullseye in the center, but do you notice that those measurements or those targets are, whatever I'm trying to say, they're all hitting the same area. So they are precise, but it is not accurate. But then this last one on the right, they're all hitting the bullseye, and they are all close to one another. So that is something that is both precise and accurate. So that's kind of the comparison and making sure you understand the difference between the two. So now what we're going to do is we're going to look at a couple of practice problems. Okay, so the first one, it says somebody is going to check the accuracy of a graduated cylinder, and they're going to fill it a couple of different times to a 25 milliliter mark. using the water delivered from a burette. Now, I will point this out because you may not know this. A burette, you haven't seen a lot of them yet, but they are a much more precise way to measure something. So the burette is more accurate than the graduated cylinder, and the graduated cylinder is more accurate than, say, a beaker. So they're comparing with a graduated cylinder and a burette here. And then they read the final volume. So what they do is they fill a graduated cylinder up with 25 milliliters. They have 5 different trials here. So they fill it up to 25 milliliters, but then they actually read over here the readings on the burette when they fill it up to the 25. So you see those measurements are different. So for each one, they get maybe 26.54, 26.51, but on the graduated cylinder, it's reading at 25 milliliters. So the average in the graduated cylinders, obviously, is 25. When they average these trials over here, it's 26.54. So what they want to know is the graduated cylinder accurate, or is the graduated cylinder precise, or is it both? So you need to be able to think through here. So I, in my opinion, would say that it's not accurate. Because if I wanted to say it's accurate, I would want it to be exactly 25 milliliters. And it's not close enough to that true value. I want it to be 25 milliliters, but the average is actually 26.54. So it's not accurate because it's not, and my description is because it's not close to true value. Oops, I'm going to put TV, meaning true value. But is it precise? Well, when I look at these series of measurements, I mean, look how close they are to one another. They're all extremely close. So this is definitely precise because the measurements are close to one another. Okay, so what we're going to look at for these is we're going to look at determining whether the accuracy or precision is high or low on these scenarios. So what we have is a couple of temperature measurements were taken. Let me get my pen again. 5 temperature readings were taken. It's at 38 degrees Fahrenheit. So again, that is my true value that I'm kind of comparing it to. Well, when I look at all those temperatures, I only see, this one's maybe a little bit close to 38, but it's not close enough. So I would say that this is very low accuracy when I'm looking at that. Now, what I'm looking for precision is I'm looking at, are those series of measurements close to one another? And in this case, no, these are low. They are low precision because none of those measurements are close to one another. All right, down here, again, same scenario. I take 5 different temperature readings. My true value is still 38 degrees. So when I look at that, again, most of those values are pretty close. I mean, this one's a little bit lower than 38, but they're still all really close to that true value. So I would say this has high accuracy. And then as far as precision, because those series of measurements are all close to one another, it is also high precision in that case. All right, and then the last one we're going to do here is talking about a student that's given a rock. That rock has a known mass of 436.8. Again, when I'm given a number like that, that means that's my true value. So this person measures the mass of the rock 3 different times, and they come up with those 3 numbers. So you are supposed to look at this and say, well, what do you think about their accuracy, and what do you think about their precision? So I'm looking at this like, those numbers are nowhere near 436. So as far as accuracy, I would say her accuracy is pretty low. So that is definitely low accuracy because those measurements are not close to that true value. But when I look at precision, what's going on with the precision? Well, I would say in that case, that's high precision because those 3 measurements are very, very close to one another. So they definitely are not accurate, but they are precise. So you kind of have to understand the difference between those two. Okay, so what I want you to do is, that's all for today. I want you to go and answer your concept review over these 2 sections. Thanks.